All right. Well, great. Go ahead. All right. So we are going into day one of PFT 105 here. We are going to start off by talking a little bit about cellular metabolism. So I got to get my notes open here, which means I just realized I opened the wrong folder. I'm rusty. I'm out of practice.
The NASM textbook, right, Brad?
Sort of. So this class is actually taught out of PowerPoints, but it will cover a lot of the physiologic concepts from your NASM textbook. Chapters 4, 17, and 2. So we're going to be covering all of those as PowerPoints. This is going to be more in depth than your textbook. So there's some information that your textbook doesn't have. This is going to be more in your regular, your regular NASM textbook. So it's called NASM's Essentials of Personal Fitness Training. That's the regular.
They want to give us in the school, right?
Yeah, we're going to get that to you guys for sure. But like I said, this class is actually taught off of these PowerPoints because these PowerPoints are more in depth than the textbook is. They're going to have more information in them. But if you want to know what chapters this corresponds with, and it's not going to be word for word right now, 2, 4, and 17, I think, are the primary ones. Oh, and a little bit of chapter 3. Yeah.
One question, please.
Yeah, please.
So if we want to study for the test, do you recommend us to print the things? What you put it in PowerPoint?
So for our tests, for Sochi tests, like homework and stuff, study the PowerPoints and my notes. You'll also notice, take a look, guys. You can see I got a little note thing over here. This is where I'm going to be talking. This is where I'm going to spend most of my time talking, actually. These notes correspond with this PowerPoint. And so I'm going to have this pulled up side by side, and then my face should be in the corner. I don't know why I moved over there. But my face will be up here. The notes are going to be below it, and the PowerPoint's over here. And that's how we're going to talk about all this stuff. So you're going to get, I forgot one last thing I wanted to show you guys. Here's how easy it is to get your notes, to get the PowerPoints, and to watch the videos. I will be sending you an email that will look something kind of like this every single day. You'll get an email from me, like I said, around 2 o'clock on average, unless my computer blows up. Sometimes it goes out at night, but generally I try to get it out at 2. And you'll notice it has got attachments on it. So here are, the notes and the PowerPoints. Here is like a little message from me. Here are links to the YouTube channel, which if you go to YouTube, you will find our program. Look at that hair. So here's the Sochi Fitness program. And then you'll notice it's got playlists for all of our classes. And when you go to them, if you go to an individual video, you will notice under resources, it's got another link to the PowerPoint, the notes, the homework. So I am sending it in an email attached to you. It is on the YouTube channel. And if you go to Canvas, it will always be on Canvas, available for download, video, notes, PowerPoints. So there is no excuse for someone who's like, I couldn't find the homework. Oh, I know you can find the homework.
Yesterday I was watching all of those kind of things. I say, okay, there's a PowerPoint of the video. There's a PowerPoint of the version PDF, and then after the notes. So I said, oh my God, it's too much.
It looks like a lot, but remember, I'm sending it out every day. Just do whatever I send you. Don't try to go ahead. If you go ahead, you're probably going to get confused, and you might learn something the wrong way, and that's what I really don't want that to happen. So, we've got it kind of measured out to go at the right time. And like I said, everything is very circular. This stuff right here, metabolism, anabolism versus catabolism, all of this stuff is going to come back over and over and over and over and over and over again. Because I've got a whole new group of students joining us in 6 weeks. You guys came in today. In 6 weeks, I'm going to have a new group of people coming in. We got to get them caught up on what metabolism is. And so you guys will hear it for the second time. They'll hear it for the first time. So that's why, we've got our resident experts here. And it gets clearer and clearer and clearer every time you study it. Rather than in a traditional school where, you study something for maybe 6 weeks at a time and then never come back to it again, and you're just expected to remember it. We like to do things very circular. We like to revisit concepts a lot.
Mm-hmm.
All right. So exercise I love this class. I love talking about physiology. So we are talking about cellular metabolism today. So when I say metabolism, a lot of times people tend to be like, yeah, it's how many calories you burn, right? Like, you're tall and skinny, you got a fast metabolism. Me, I've got a slow metabolism. It's like, well, let's go ahead and talk about like what that actually means, right? When I say metabolism, I want you guys, our objectives for today, we want to be able to define metabolism and its two components, its two directions, anabolism and catabolism. So metabolism is like the big version, and then it goes either that way or that way. There's no middle one. And that's, anabolism and catabolism. We want to be able to understand what's taking place during what's called an oxidation reduction reaction, which is hard to say, but basically talk about like how your body is going to oxidize molecules to, release like a big amount of energy. We're going to talk a little bit about cellular respiration. We talk about like how, you're breathing in air right now and you're spitting out CO2. Air goes in, CO2 comes out. Oxygen, CO2, oxygen, CO2. You are respirating. Well, what's funny is on a cellular level, every single one of your cells is doing the same thing. It's taking in a little bit of oxygen, it's spitting out CO2. The reason we breathe is because all of our cells are breathing on a smaller level. We are nothing more than a big, big, big group of cells, and we kind of act like cells, which I think is really fun. Then we'll talk a little bit about what's called glycogenesis and gluconeogenesis and lipolysis. Basically, that's the difference between like producing glycogen or breaking down protein or breaking down fats. So we're going to talk about how we use proteins, fats, and carbs. And then we'll talk a little bit about like what's called hydrolysis, which is a process by, using water to break stuff apart. Or we'll talk about dehydration synthesis, which is how we use water to attach stuff. So water is pretty amazing. And we're going to talk a little bit about that. And then finally, we'll talk a little bit about our metabolic pathways, how we produce energy in different scenarios. Are you jogging? Are you sprinting? Are you jumping? Those are three kind of different things. They require different types of energy. So we'll talk about like how that works. So that is our objectives for today. Give you a little general overview here. Chemical reactions, when we talk about like metabolism, our actual definition of the word metabolism, which we're going to see in the next slide, is any and all chemical reactions that take place in the body. So it's not just how many calories you burn, it's all chemical reactions that take place. Like right here, right? I've got a coffee and, I like my coffee with a little bit of milk and a little bit of sugar in it. So this has got a pretty good mixture of proteins, fats, and carbs all in it at the same time. And so what first has to happen is my digestive system has to deassemble all of those proteins, fats, and carbs, right? So it has to take all those ingredients, and it's like a protein is complicated. So it has to break it down into what are called amino acids. Carbs are also pretty complicated. So it has to break it down into individual sugars. And fats are these big, long chains. And so it's going to break those down into little shorter chains. And so now I've got just ingredients. So now what's going to happen is it's going to get into my bloodstream and it's going to go somewhere throughout my body, right? So so chemically, right, my stomach acid broke a lot of that down. It used bile to break apart the fats. It used brush border enzymes to break up my carbohydrates. You know, all this, even my taste buds, even my spit, my saliva mixes with some of the sugars that are in this coffee and break those down. So all that's getting broken down, it's getting deassembled. Some of it's mechanical, you know, like if I were eating something rather than just coffee here, you know, if I had like a granola bar, I like chewed it, right? I'd be physically breaking something down, but chemically, there's a lot of stuff getting broken down, right? So that's part of my metabolism. Then it gets into my bloodstream and my body goes, oh, that's perfect. We needed some protein because we worked out this morning. We're going to take that protein and we're going to put it on the quads because it was leg day, right? So then it's going to reassemble and fix any of the damage that I created this morning. That chemical reaction that makes that take place is part of my metabolism. Meanwhile, some of those fats that I consumed, maybe that's going to be burned up for energy to fuel that, you know, in order to allow that protein fixing to occur, it needed to have some energy in order to pay the, you know, construction workers, right? And to pay the money, to pay the energy to fuel the repairing of my muscles. And so maybe that comes from the fat that's in my coffee. And then that sugar is going to get stored for energy later so that when I work out tomorrow, you know, I have enough energy to be able to get that done. So that's a much more complicated version of metabolism, right? We want to understand that like it's all of these chemical reactions. As your cells are dividing and copying and making new versions of themselves, you know, they got to build that from proteins. And so we have to be able to take proteins and assemble them together. You know, unfortunately, it is not as simple as like you go do a bunch of push-ups and now suddenly you damage your chest muscles and your body's like, well, we need to make more chest muscle. And then you go eat a chicken breast and your body goes, oh, a chicken breast, that's perfect. Put that right here. You know, it's not quite that simple. But it's going to take that chicken breast, it's going to break it down into amino acids, and then it's going to reassemble them in a slightly different shape. U-shaped, right? Or me-shaped if you know, if I'm the one eating it. And so what kicks off that chemical reaction? Well, luckily there are these things called enzymes that allow that to happen. So enzymes actually are proteins, and their job is to basically ignite chemical reactions. So if you want to think of, you know, a chemical reaction as like your car, right? So, you know, if I put my key in my car and I turn the ignition, it burns up a bunch of fuel, you know, ignites all the gas in my gas tank and propels my car forward. So, you know, the gas in my car is kind of like carbohydrates and fats, you know, it's my fuel. But I can't use any of that gas until I start start my car. So your key, the key to your car doesn't have any energy, right? You know, it's not what's propelling your car forward, but your car cannot use any of that gas until you turn your key, until you start the ignition. So you can think of the key as like an enzyme and think of the fuel in your car as carbohydrates and fats. So you put in, you turn, you know, that enzyme activates your body's ability. Suddenly it starts kicking off metabolism, and then, you know, you're traveling to the store or whatever. So metabolism, by definition, this is one of your textbook definitions here. It is any and all chemical reactions that take place within the body, right? Now, when I say any and all, there are two categories of metabolism, right? So like as organisms grow or maintain body functions or release energy, eliminate waste, you know, your body is either breaking stuff down or it is building stuff up. And that is where we get anabolism versus catabolism. So these are the two directions that happen, right? And one of the things that we'll sometimes say, and actually if I look this up here, I look this up, I'll probably see a chart pretty quickly of what I want to. No, maybe not. This always happens. I always assume that I'm going to see something on the internet and then I never actually find it. All right, well, I'm going to make a chart. So one of the things that we tend to say is that catabolism fuels anabolism, right? So if we think of like anabolism as the building up, right? And we think of like catabolism as the breaking down, right? So when we think about this, oops, gosh darn it. Oh, hold on. When we think about this, you know, you can't build something up from nothing. So you kind of have to start by breaking stuff down. You gotta start with catabolism, right? You gotta take a donut and break it down into sugars for energy. So what we'll often say is that, you know, catabolism will fuel anabolism, but both of them together, right? Both of these processes together make up your overall, I'm just gonna write this out this way, make up your overall metabolism. Ugly chart. But so what we're gonna do is we're gonna break food down to have ingredients to build us up, right? So if you take that chicken breast, right? If I were to eat a chicken breast after doing some push-ups, my body is gonna catabolically break that chicken breast down into its ingredients, into its components, which are called amino acids, right? And amino acids are going to get assembled in a different order that makes up muscle tissue, and it's going to repair, you know, my pectoral muscle. And my body is going to kind of assemble that. So, you know, I ate something, I broke it down, and now I built it back up. So those are the two parts of metabolism. And you're going to want to get these memorized, right? So on a different level, right? We know that we know that anabolism is building up, and we know that catabolism is breaking down. Well, in order to kind of understand that a little bit more effectively, we kind of need to look at like, how are they getting assembled? Like, how are we taking, you know, if I've got an amino acid here and I've got another amino acid here, how do I link them together? How do I get them like attached? Well, what's kind of funny is that your body actually uses a process called dehydration synthesis in order to make that happen. It actually pulls the water out of some of this amino acid, and it pulls a little bit of water out of this amino acid. And because there's no more water, you know, these guys actually get attracted to each other and they link. And your body will do that over and over and over and over again until eventually it has assembled a new full protein. Meanwhile, if your body's trying to break stuff up, like, how do you break stuff up? Like when you're doing the dishes, right? You pour some water on it, leave it in the sink, and then that water starts breaking everything up, and then you can just wipe it out, right? You know, if you were to take a slice of bread and drop it in water, the reason that bread inflates and then eventually flakes apart and falls apart is because all of those little water molecules are shoving themselves in between all the little molecules of bread, and it's breaking them apart. That is a catabolic process. So let's go ahead and watch a quick little video here. We got a fun little video that's going to kind of explain this. This is like the better version. This is like the better version of my version of class, this video here, because it's actually, they've got all this big fancy equipment that lets them do stuff.
Textbooks define metabolism, a topic in biochemistry, as a series of chemical reactions that take place inside of our bodies to sustain life. Now, this is a pretty broad definition of metabolism. So in this video, I really want to break this definition down to a more workable understanding of what metabolism really is. So first, I'm going to introduce another arrow in this diagram like this and say that really the requirements of life, let's say in a human being, such as, you know, maintaining a constant internal temperature, reproducing, growing, and all that jazz, all of that ultimately boils down to the body's ability to utilize 4 essential biomolecules. And these 4 essential biomolecules, or as they're sometimes known as macromolecules, are proteins, fats, carbohydrates or carbs, and nucleic acids like DNA and RNA. And ultimately, all of these biomolecules perform different life-sustaining reactions inside of all of the cells in our body to ultimately promote life. So as you can see, we've already begun to break down this definition of metabolism. Essentially, what we're saying here is that metabolism is really the study of how we're able to obtain these important biomolecules to sustain life. So how do we obtain these biomolecules? Now, the simple answer to this question is, of course, that we eat food to obtain all of these important biomolecules. But there's an important word of caution here, which is that since most food comes from living organisms like plants and animals, these plants and animals also contain an array of proteins, fats, carbohydrates, and nucleic acids, but not necessarily in the same flavor or configuration that our bodies would prefer. So what do our bodies do instead? Well, in our bodies, we go ahead and eat the food. It's a very large head there, but you get the idea. And in our bodies, we break down this food through a process called digestion into the component parts of all of these biomolecules. So what do I mean by component parts? Well, the smallest subunit of proteins is called an amino acid, and our body breaks down all the different types of proteins that we digest into individual amino acids. And the same pattern continues for the rest of the biomolecules. So in the case of fats, we're talking about fatty acids, which are the smallest subunits of fats. And then for carbohydrates, which are long chains of sugars, one of the most common subunits of carbohydrates that our body loves is called glucose. So I'll go ahead and write that here since you'll be seeing it a lot in the discussion of metabolism. And then finally, for nucleic acids, we're talking about nucleotides. So at this point, you're probably thinking, well, okay, I understand that our body can't use the same macromolecules found in food because maybe they're not in the right configuration, but how does breaking them down do anything for us? Now, the key here is to recognize that in our body, there's actually a delicate balance going on between the processes of breaking down molecules, such as in the process of digestion, and then taking these products and building them back up. So essentially, you can see all of these subunits or monomers as Lego pieces that we're essentially reconstructing to build the right configurations of proteins, fats, carbs, and nucleic acids that our body needs. So that's really the key idea here, which is that metabolism is a balance between breaking things down and building them back up in our body so that we can customize, so to say, what type of macromolecules that we create. And just to throw in some vocab words, biochemists call the process of breaking down molecules in our body catabolism, and a similar sounding word called anabolism is used to describe the process of building molecules back up. And the way I kind of like to remember this is looking at the first letter of each of these words. I think of C, I think of cutting molecules up into tiny pieces, so breaking them down. And then for anabolism, A, I think of as like the apex of like a building, for example. So we're building something up. Now this seems all fine and elegant, but there's one more issue that we need to contend with, which is a consequence of having to balance breaking things down and building them back up. And that is that this process of building molecules back up requires energy, which I'm kind of indicating here by these yellow lightning bolt stars. So the question I want to answer in this last part of the video is, where does this energy come from? Now, the answer to this question is that, well, we also get this energy by eating food. So how does that work? So first, recall that the energy currency of the cell, and I'm going to go ahead and erase this just to give us some more space. The energy currency of our bodies is a molecule called ATP, or adenosine triphosphate. And this high energy molecule, as it's often referred to, when it is broken down into ADP, so it loses a phosphate group, it releases usable chemical energy that can fuel energy requiring processes in our body, such as the building up process of metabolism. Now, in order for this process to continue nonstop in our bodies, ADP must be regenerated into ADP. And that is where food comes in. So remember that we digest our food into all of these subunits, and some of these subunits, such as glucose and fatty acids mainly, but occasionally amino acids, I'm going to put that in parentheses, can essentially be used as fuels in our body. So just like wood, for example, is a fuel for a burning fire, which produces heat, these fuels in our body can essentially be broken down even further to produce the energy that's necessary to convert ADP back into ATP, and thus allowing this cycle to continue. And just to throw in another vocabulary word that you'll probably see, this process of taking these fuels, which I've indicated with this asterisk, and breaking them down into usable energy is a process that's referred to as cellular respiration. And recall that because cellular respiration involves breaking down things even further, it's also a catabolic process. So it falls under this category of catabolism. And just to tie everything here together at the end, notice here that another way to interpret this cycling between ATP and ADP is to say that catabolism fuels anabolism. So what do I mean by this? Well, essentially, catabolism, such as the process of breaking things down and extracting energy through processes of cellular respiration, is coupled with this process of building things back up. And so in essence, one relies on the other. And as you can probably guess, these processes are really tightly regulated in our bodies, because obviously you wouldn't want to be breaking down something while you're building something back up. And in fact, just to give you kind of a preview forward, catabolism and anabolism are often regulated, so controlled, through the use of hormones. So I'm going to write here that hormones are a form of regulation and tell the body whether it should be in a catabolic or anabolic state.
Okay. So hormones, by the way, are, and I'm just going to mention this briefly. So hormones are meant to be, part of your body's control system. Your body controls itself through your nervous system. I mean, your nervous system is controlling, me raising my arms right now, right? That's my nervous system. But like how quickly I release energy from my cells, like how hungry I feel, or how, how much energy I feel like I have, a lot of times that comes down to your hormones, and that's why it's super important to get enough sleep so that your body can produce enough of those hormones every day. It's why it's so important to try to be stress-free in your life, because that's going to help you create the right hormones, and to give yourself enough fuel.
I got a question.
Yeah, what's up?
The hormones, male hormones is different from the female hormones. That's why we got to eat different type of things. You know what I'm saying?
So what's funny is males and females have the same hormones, actually. They're identical, but the levels are different.
Levels.
Yeah. So for instance, men make way more testosterone, about 10 times as much testosterone as women do. And testosterone is a very anabolic hormone. Remember, anabolism is all about building stuff up. And that's why men tend to be larger than women. We have larger muscles. We have a little bit denser bones, generally taller, right? And that's because that is an anabolic hormone. Women produce more like estrogen, which is also, anabolic. It can act catabolic in men, because we aren't really supposed to have very much estrogen. But there's a lot of hormones throughout the body. There are, those are what are called those are your sex hormones. Those are what give you, sex traits, and, they're things that you produce, in like whatever like sex you are, right? But there's also hunger hormones. For instance, there's 2 hormones in your body that tell you whether or not you are hungry or if you're full. One of them is called leptin. That one is in charge of making you feel full. Do you guys remember growing up and your mom would say, chew your food, eat slowly, because, or if you've ever heard somebody say this, they're like, you should eat more slowly because it will give your body time to realize that it's getting food, and then you can eat less and they'll tell people who are on diets, they're like, you should eat more slowly because then you'll be less hungry. And that's actually somewhat true, but it's not because your brain, it's actually because of your hormones. Your body will start producing, when you give yourself food, your body will produce a hormone called leptin. And that signals to your body the fact that it's getting food, and that's going to trigger the production of digestive stuff, and it's going to slow down the hunger stuff. Meanwhile, if you don't have any food and you start to like lose energy, your body will produce a different hormone called ghrelin. And that's the one that makes you hungry. It's easy to remember because your stomach is growling, right? But that's what ghrelin is. And ghrelin makes you feel hungry. So leptin makes you feel full, ghrelin makes you feel hungry. Testosterone, estrogen, we've got insulin is a hormone that your pancreas makes. If you have a client who is a diabetic, either their body doesn't produce enough insulin or their body has become resistant to insulin. But insulin's job is to pull sugar out of your blood, and that's a hormone. Glucagon is the opposite of insulin. Its job is to put sugar into your blood. So we got a lot of different hormones. We've got cortisol, which is a stress hormone that you often hear people are like, cortisol, you got to not make as much cortisol as possible. But to be perfectly fair, from a scientific standpoint, cortisol is a good thing. Cortisol is it's a stress hormone. It makes you feel stress, which sounds bad. Because we live in a world full of stress, but if you were like a cave person and a bear jumped out of nowhere and was like, brah, and you didn't make any, if you didn't make adrenaline and if you didn't make cortisol, you'd be like, oh, what a fuzzy animal. Oh, it's mauling my leg. Bummer. Like you wouldn't have any reason to like run away, So we like stress hormones, but the problem is we live in a world where biologically, my brain doesn't know the difference between being attacked by a bear and paying my bills on time, So unfortunately, we live in a world where we make way too much stress hormones. But anyway, those are hormones. They're going to regulate, how fast your metabolism is burning. Is your metabolism really, really fast? Well, maybe you're producing a lot of hormones. Or is your metabolism really slow? Maybe you're not producing many hormones. Is your body building muscle easily? Well, maybe your body is producing anabolic hormones. Or do you have a really hard time gaining, muscle because your body is breaking any muscle that you build back down, or it's resisting trying to build it up because it's producing more catabolic hormones? It's all going to be a little bit different, and it's all going to come down to how you treat your body. So, that is the process of metabolism: catabolic reactions and anabolic reactions. Now, how does our body build this stuff up or break this stuff down, right? I did that in the wrong order. Break this stuff up. Build stuff up or break stuff down. How does your body do that? Well, there are 2 sort of processes that allow that to happen. They are both chemical reactions, okay? And so these chemical reactions, the first one is what is called dehydration synthesis. So the process of building complex molecules from simple molecules, right? If I took something simple and I built it into something complex, that's anabolic, right? If I took a whole bunch of Legos and put them together and now suddenly I've got like the Death Star from Star Wars, right? That was a whole bunch of simple pieces into something very, very complex, right? That's anabolic. In your body, if you take amino acids and add them together, that is anabolic. So how does it happen? How does it actually occur? Well, take a look right here. These are actually sugar molecules. So this is a molecule of what is called glucose. And glucose is what all carbohydrates are made up of. So bread, sugar, honey, fruit, vegetables, all of those are carbohydrates, right? And what a carbohydrate is it's a big long chain of glucose. If it's a really big, complicated chain, that is what we call a complex carb. If it's a really short, very simple chain, that is what we call a simple carb. Sugars are simple. Things like whole wheat bread, pasta, vegetables, and fruits tend to be a little more complex. So when you look at it, right, this right here is an individual sugar molecule, and this is an identical individual sugar molecule. Now, I need to be able to have access to these sugar molecules at all times. Our bodies prefer to use sugar to produce energy. So remember, the big thing that we're trying to make earlier, she was talking about it in the video. She mentioned ATP, adenosine triphosphate. We're going to talk more about ATP later, but ATP is basically the currency that runs your body, right? Like, you know, if there's a video that we're going to watch, and the analogy that he uses is like, if your body was like the United States, ATP is basically like credit cards. it's how we pay for everything. And so, our body, what gives me enough energy to raise my arm here is my body created a whole bunch of ATP explosions to let that happen. The things that are keeping me breathing right now, the things that are letting you process information, all of that is requiring millions and millions and millions of molecules of ATP. Just like your car, ignites gasoline to create explosions, and then it captures those explosions to propel your car forward. Your body creates little ATP explosions, and it captures them to propel your body. So how do we produce ATP? Well, our body can do it with either breaking down carbohydrates, or it can break down fats. And so if I know that I can break both of those things down, I probably want to have some stored versions of those carbohydrates, and I want to have some stored versions of those fats. And it's pretty easy to see the stored fat, it's all over your body, probably on the love handles down here, right? We've all got a little bit of like stored fat on our body. That's great. All that fat, if my body's like, hey, I need to produce some energy, I'm going to take some of that fat, break it down, and release some energy, right? Well, your body also does that with carbohydrates. So I got a question for you guys. Andre, anybody, has anybody in here ever done like a low carb diet? You ever tried like a low carb diet?
Yeah, I have.
What is it?
You talking about like a keto diet?
Nah, I mean, yeah, keto is an example of low carb, but just generally low carb.
What does it mean? What are you asking?
So if you've ever tried like a diet that, you don't eat very much bread, you don't eat very much pasta.
Yeah, I do that.
Yeah.
Because, for my age and for my metabolism, like you say, in the time is passing the time, the metabolism of the people is changing.
Yeah.
And for example, in my case, I have I start produce too much hormones. So yep. I need to change my habits of food. So I stopped to eating too much pasta, too much rice, too much beans. I eat more vegetables. I get more energy. I eat more fruit. And I like to do exercise. Well, just now I stopped because I have the COVID, but I like to do exercise, and this is helping me to get the energy all the time. And in the night, I can sleep well.
Love that. So, rice, beans, pasta, all of those things are big, complex carbohydrates. And what will happen a lot of times, and tell me if you guys experienced this, when you first went on your low carb diet, did you notice that you lost weight like that really quickly in the beginning?
Yes. Yeah.
Yep.
Yeah, you lose weight, but you get more energy too.
Maybe, yeah. And we'll talk about that in a little bit. But generally what people will find is they'll go on a low carb diet and they'll lose weight very, 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 very quickly in the beginning. And then it slows down. And that's usually when people get discouraged and then suddenly they fall off the wagon. But here's why you lose so much weight so quickly. So your body stores carbohydrates throughout your whole body. You actually have carbohydrates stored all over you right now. You've got some stored in your muscles, right? So I've got a ton of carbohydrates stored in my quads and here, and it's stored in this kind of wet, soupy mixture that we call glycogen. So you have all this glycogen running throughout your body. And then a lot of it is also stored in your liver. Your liver also has a whole bunch of glycogen in it. And so what will often happen is people will lose a ton of weight really quickly, because what will happen is their body will burn through all the carbohydrates they've been storing, and they'll lose a couple pounds almost overnight. If you skip meals for a day, you'll lose a ton of weight the next day, because your body will actually eat through all those carbs. Now, that doesn't necessarily mean you lost a lot of like body fat. It just means that you lost some body weight. Charlie, do you have a comment?
Oh, no. I'm sorry.
Okay. So that's a really common thing that will happen to people. I can't remember how much it is, but let's see, how many pounds of glycogen does the body generally store? So yeah, you usually have about 400 grams of glycogen. So, the glycogen itself is only 400 grams worth, right? So that's only about a half a pound. So that's not even a full pound of weight. So where does the rest of the weight come from? Well, there's a lot of water stored in glycogen as well, which is also why when you go on a low carb diet, you'll notice you look in the mirror and you're like, gosh, my abs look awesome, at first. So there's a lot of water in there. So that's what glycogen is, right? It's all this stored carbohydrates. Now, we like those stored carbohydrates, by the way. We're a big fan of having stored carbohydrates, because that's what's going to give you energy if you don't get a meal. When you get, like, let's say you just didn't have time to eat breakfast or lunch, it's been a really busy day, you haven't eaten in a couple hours, you've got stored energy in your body. So your body can go, all right, I'm going to release some carbohydrates from the liver. Maybe I'll release some from the biceps and the quads and the glutes. Generally it's nearby. And then that's going to allow you to have enough energy to propel you throughout the day, right? So, that releasing of glycogen is catabolic, right? So now, how do we store it? Like let's say you burn through all your glycogen, you've got none left in your body, and now you're getting kind of hangry, you're getting that, you're like, I haven't eaten in a while and I'm going to lose my temper, So now you're out of glycogen, but you're still doing work. How does your body refill all that glycogen? Well, it has to anabolically build it back up. So you're going to eat, let's say, some vegetables, right? Let's say you eat like a bowl of broccoli, which has carbohydrates in it. That is going to get broken down by your body. And then you're going to have individual sugar molecules, which we call glucose, right? That's this molecule right here. This is glucose. And that glucose is going to pass into your bloodstream. And then another one's going to pass into your bloodstream. And your body's going to go, perfect, we needed some carbohydrates. And it's going to link them together and store them in your liver. And like I said, throughout all the muscles in your body. So how does your body link them together? What does that process look like? Well, that process is referred to as dehydration synthesis. Okay, dehydration synthesis is the process of building up complex molecules by dehydrating two simple molecules. So I've got a simple sugar right here, that's glucose. And I got another simple sugar right here, which is also glucose. Now, you will notice, take a look here, guys. Do you see how this glucose molecule has what's called an OH pairing right here? So that's a little bit of oxygen, and that's a little bit of what's called of hydrogen, right? So you got a little bit of oxygen and you got a little bit of hydrogen. That's an OH pairing at the end there. But then look at the other side. You'll notice at the beginning, and actually we can even just look at this one, it's got an HO pairing. It's got hydrogen on this end and oxygen on this end. So now if you look at that, I've got an O, I've got an H, I've got an H, and I've got an O. So remember that water, right? Water is nothing more. This is the chemical formula for water, right? So what that means, it's H2O, that's water, right? So what that means is that there's two hydrogens and 1 oxygen. So that's actually H2O. It's H plus O. So if I go over here and I look at this molecule and I take that H away and I take an H away over here, now I've got 2 H's, and then I also steal the O from over here. So if I steal this H and I steal this H and I steal this O, and then I just kind of put it off to the side, now all that there's left is this little oxygen molecule. And now these 2 separate molecules are going to be attracted to each other, and they're going to go, and they're going to link. And that is you sucked some of the water out, you dehydrated it, and it synthesized and attached itself together. That is how your body assembles proteins. It's how your body assembles carbohydrates. It's how your body assembles anything. It sucks some water out, and then 2 little small things are attracted together. So if you did that again, now you got 3 things, and you did it again and again and again and again and again. Now you've got this big, long, complex chain, and your body took something simple and used it to build it up. Does that make sense, everybody? How are we feeling about that?
Yeah, I understand what you're saying, but we are needed to learn and all those things too.
Not necessarily. You're not really, you'll have like 1 test question related to dehydration synthesis. Like I said, this is more in depth than your regular textbook, but I want you to kind of understand a little bit about this, even if you don't necessarily know this inside and outside, and you don't feel like you can explain this to your clients. That's okay. I want you to kind of have a good idea of what it means, because what in later classes, we're going to talk about how to assemble proteins. And I want you to understand, it's like, okay, I remember we talked about assembling proteins, basically we're talking about this so that it doesn't, it doesn't seem like magic. You know what I mean?
No, I know it is not magic. It is something simple, like sentence things. But I want to know if in test we are needed to explain something of this.
You will not need to explain this to your clients. No, not necessarily. Some of you may want to, which is great. But you don't need to be an expert on this. This is, like I said, it's more in depth than it needs to be. Think of Sochi as you came to us and you said, hey, what time is it? And then we taught you how to build a watch.
Oh, okay.
That's how I like to think about it. You asked me for the time, I taught you how to build a watch. So that's dehydration synthesis. That is an anabolic process. That's how our body builds stuff up. By the way, this also happens in proteins. So proteins are a little bit different. Like these are carbohydrates. Carbohydrates are held together with a little oxygen molecule, same as proteins. But the bond is kind of weak here. This is actually a very simple bond that's pretty easy to break, which is a good thing because we want to be able to break protein. We want to break carbohydrates down really fast. Proteins are a little bit more complicated. Proteins are held together by what's called a peptide bond. So a peptide bond's a little bit different. It's a little bit more complex. It's held together with a little bit of like nitrogen, and it's just slightly different. And they look like this. So this picture's a little bit different looking, but this right here is an amino acid. And then this one right here is a different amino acid, right? So we got 2 different amino acids here, and I want to link them together so I can make a new protein, right? Let's say I'm making up, let's say I get like cut on my cheek, right? And my body needs to make like new skin right here, right? It's going to assemble amino acids in the shape of skin. It's going to assemble them all together to make up new skin cells. So what it's going to do is it's going to dehydrate this amino acid, and it's going to dehydrate this amino acid. It's going to pull up the hydrogen from here, and it's going to pull out the hydrogen from here, and then it's also going to pull out the oxygen from here. And there you go, 2 hydrogens and 1 oxygen, H2O. So I'm left with an extra molecule of water afterwards. And then I assemble these 2 together, and you will notice they're held together. There's the oxygen, but it's kind of a little more complicated. See how much longer this like link is? That's a peptide bond. It's a little bit more complicated. It's a little bit more difficult to break down, which is a good thing. I don't want to break down my proteins easily. I don't want my body to break apart you know, very, very easily. You know, if it was too easy, if it was too easy to break this down, you know, we would all of a sudden like, you know, you would jump into a pool and all of a sudden you would dissolve. So luckily peptide bonds are a little bit more complicated than just a simple carbohydrate oxygen bond. Actually, guys, we just had my boss join us. Jessica just hopped on the call. What's up, Jess? Oh, I don't know. She might not have audio.
So I got a question.
Hey, you know what? I was just checking in with everybody, to all our new guys, to make sure everybody made it in.
I love this. You should join my calls more often. It's good to hear your voice.
I know. Happy New Year, everybody.
Happy New Year.
Outside walking my dog right now.
Happy New Year.
That's awesome. We are talking about dehydration synthesis.
I could tell when I logged in that you
not
were
as
on
fun as walking a dog.
Do you have anybody that's missing this morning?
I'm not 100% certain who is evening versus who is morning.
Okay.
I don't have a list of who's who, but of all the newbies, I guess I know that I talked to is it Isaiah or is it Isia?
Isaiah.
Oh, I just saw your text message. Shoot. He, I know, is coming to the evening.
Okay.
So Isaiah, Christopher, and Callie. Callie is the one that I'm still having trouble getting a hold of.
All right. I'll let Amy know. No problem.
I've texted her, I've called her, I've emailed her. I haven't heard anything.
Wherever he wants. Okay. All right. Sounds good. I will have Amy reach out to Callie, and I'll let her know the other two are going to be there in the evening. Okay.
Yeah, I'm pretty sure the other two are going to be evening students.
Thanks, you guys. Have a great class.
Yeah. See ya.
Bye.
Hey,
Noel, you have a question.
So a peptide bond is when two come together and it heals.
Yeah, you can think of it as healing, but it's also just any time any protein is held together with all proteins are held together with a slightly more complex bond than carbohydrates. Carbohydrates are held together pretty weakly. Proteins are held together really strong.
Okay.
So healing would be part of that, right? Like if I assembled new protein to heal, like if I have like a scar or something, right? Making new tissue, that would be made of proteins. So that would be those would be held together with proteins. So that would be a peptide bond. Your steak is held together. It's all proteins. That's all made of peptide bonds. Any protein is a bunch of amino acids, and they're all linked by peptide bonds. By the way, guys, that's why you have stomach acid, because proteins, like if you drop a steak in water, it doesn't dissolve. You drop bread in water and it dissolves, right? Your steak needs to sit in acid, and that's what breaks apart those peptide bonds. That's why you have stomach acid. We'll talk about that tomorrow, actually. Did you have a question, Guadalupe? Yeah, it's much slower. Yeah. No? Okay. Sorry, I just saw your thing light up. All right. Okay, so that's either way though, assembling them together. So that we talked about, breaking them down. Assembling them together though, that is dehydration synthesis. You pull the water out of both of them and it links them together. So then we got to do the opposite process. So that was all building stuff up. That was anabolic. Well, now we need to break stuff down. How do we break it down? Well, we're going to use the exact opposite process here in catabolism. This is called hydrolysis. Oops. So dehydration synthesis is building complex molecules by dehydrating and pulling water out. Hydrolysis is breaking stuff apart, breaking it down by shoving water in between two molecules. So this involves the decomposition of molecules. You're going to break them down by splitting those molecules with water. So, if before I had two separate molecules and I pulled the water out and that linked the two molecules together. Well, guess what? If I shove a water molecule in between these two, that's going to break them apart. So when we look at that, right, let's look at, we'll do a little paint version here. I'm going to draw a very simple, oh my God, I can do this. It's actually really nice. And then draw another one right there. All right, so these are held together right now. So this is held together with a little bit of oxygen, right? There's some oxygen holding these two together. So here's a carbohydrate. This is now a slightly more complex carb. Well, if I had a water molecule over here, right? Which again, oh wait, actually, I've got one sitting there. So if I've got a little water molecule over here, and I take this H and I shove it right there, and I take this H and I shove it right there, and I take this O and I put it right there, well, guess what? Now I'm going to be left with two separate sugar molecules, right? I've got one that's got an H and an O, an H and an O at the end of it. And I got another one that's got an O and an H. And they are separated now. So that is hydrolysis. Hydrolysis is shoving water between things to break them apart. Now, not everything breaks apart very easily in water. For instance, like I said, proteins they're a stronger bond. So simple water is not going to break up protein by itself. Give it enough time, it will, but you've only got a couple hours to digest your food. So how do you break those proteins down? Well, you're going to usually need something to kick off that chemical reaction, right? So that is where enzymes come in. Now, enzymes actually are proteins. They're an example of a protein, but they're a special protein, and there's all kinds of them running throughout your body. So for instance, who in here is lactose intolerant? Who gets like stomach problems when they drink milk?
Yeah, me.
Yeah, I remember we talked about that. Anybody else?
What is it? Can you repeat it again? What is it?
Lactose intolerance.
Oh, no. Well, just now, a little bit, not that much, but because before I was drinking even 1 liter every day.
Okay, fair.
Take enzymes, like lactose enzymes.
Yeah. So if you are lactose intolerant, what that means is your body didn't mutate in order to be able to drink milk. So you can take this stuff called lactase, and lactase is actually it's actually an enzyme. It's a lactase enzyme. So lactase is an enzyme that some people's bodies make, and it allows you to break up the sugar molecules found in milk. But some people don't make it. In fact, actually, Noel, and this is what's kind of funny, being lactose intolerant means that you are more normal than somebody who is not lactose intolerant. So if you can drink milk and it doesn't cause you any problems, you are technically a mutant. Like me, I don't have any problems drinking milk. So it's a mutation that happened, centuries ago. Some humans just randomly evolved this enzyme that allowed them to drink milk. But most people in the world are lactose intolerant. There are a much larger percentage of people are lactose intolerant. In fact, let's find out. Let's see here. What percentage of the world is lactose?
We used to drink it like a baby when we was little, you know what I'm saying?
Well, you drank human milk as a baby, which doesn't have the same sugars in it as cow's milk. But here it is, 68% of the world is lactose intolerant. Most people don't have that enzyme, which is kind of unique. It's a unique mutation that happened. Kind of a lame mutant power. I would have rather had like flying or something, but hey, I'll take it.
Well, I think most of the things of this happen because all the food is changing that much. and they using them cans and no natural fruit, no natural substances, I think.
Maybe. So yeah, so so what you're missing is this enzyme. So basically what happens when you're missing this enzyme, the lactase enzyme, you might drink some milk or eat some dairy, and it gets into your digestive system, and then your body doesn't have the tools to break it down. It tries to use hydrolysis, but it just doesn't work very well. It can't really kick off the reaction to break those molecules apart. So then large sugar molecules, which should be small by this point, they're too big to get into your bloodstream. So your body doesn't absorb them. So then these large molecules keep heading through the rest of your digestive tract. They never get absorbed. And then they get to your large intestine. And your large intestine is full of gut bacteria. And it's good bacteria, by the way. Like a lot of times we talk about bacteria is bad. This is good bacteria. But it is bacteria, which means it's a living creature that eats and, goes to the bathroom just like any other living creature does. And there's millions and millions of billions of them actually that live in your gut. And all of a sudden you send a big giant sugar molecule down there like milk, and then all that bacteria is like, oh my god, look at this feast, and all that bacteria starts eating that milk, and that bacteria, like I said, it's like an animal, it eats and goes to the bathroom, and that's why all of a sudden it builds up a lot of gas inside your large intestine. That's why it causes like a lot of stomach cramping and abdominal pain, because your body never broke that sugar down, because it didn't have the enzyme necessary to kick off a chemical reaction. And so because there was no chemical reaction, it never got broken down. And so people who have that enzyme, it never makes it to the large intestine. And that's why you tend to not have that cramping problem. So enzymes, they actually are proteins, but they are proteins that are in charge of kicking off chemical reactions. They coordinate chemical changes, right? They kick off, right? How do I make this whole hydrolysis thing happen? Whoops, did I close it? Oh, I did. How do I make hydrolysis happen? An enzyme can make it happen. It'll kick it off. So again, think of enzymes as like the key to your car. Your key has no energy of its own, but it allows you to use your gasoline in your car. It's what starts your ignition. That's kind of how enzymes act inside your body. And they actually call it a lock and key mechanism. So this isn't my analogy. I'm stealing this from people who are smarter than me. You've got all kinds of different chemical reactions, whether you are building up carbohydrates or building up lipids or proteins or breaking down carbohydrates, lipids, or proteins. Enzymes are going to coordinate how fast those actions take place. So that's sort of the process of like metabolism. That's catabolism and anabolism. Let's go ahead and move past that. And we're going to talk a little bit about like energy now. So moving into a different direction now, pivoting the conversation. The ability to do work, right? We are basically, all of our energy, and this is what's kind of funny, all of the energy that allows you to do everything you've ever done and everything that has ever happened on this entire planet, all of it, human history and before, all of that energy came from the sun. So the sun put a whole bunch of energy on the planet, and then that energy has transformed into different versions, right? Basically, a plant took in that energy, spit out oxygen, spit out some, other ingredients. And then those ingredients got changed until eventually they became, the metal in this spoon. They became the energy that's allowing me to talk right now, which is crazy if you think about it and gets really complex. So we're not going to talk about that. But you are going to take stuff and you're going to convert it into energy. And we get our energy from food. you're going to take a hamburger. Let's look at a hamburger. A hamburger is a perfect example of like all the energy that you would find in order to do stuff. So it's got a little bit of bread. It's got veggies on it. It's got some protein. It's got some dressing like ketchup or maybe mayonnaise or whatever you're putting on your burger. So there's proteins, there's fats, there's carbs, there's vitamins, there's minerals, right? There's all of the stuff, and there's some water in there. There's all the stuff necessary to maintain human life inside that hamburger. Now, whether or not it's healthy is a totally different conversation. But regardless, that hamburger has all of the ingredients necessary to maintain life. Until you get too much cholesterol and it causes problems. But you can break the proteins down, you can break the carbs down, you can break the fats down, and the fats and the carbs can both be used immediately to give you energy to do stuff, to do work, right? So I can turn that hamburger into this conversation right now. I can turn it into the movements that are allowing me to like walk around. I can turn it into lunges. I can turn it into squats, right? My body's going to take all that energy and transform it into work, right? It's what's keeping my digestive system moving right now, right? So chemical energy release, right? Whoops, crap, I closed my PowerPoint. Chemical energy release, I gotta go back to that. Is what happens when the bonds between like molecules are broken down, right? And then when that happens, a bunch of energy is released. So, if I look at this, if I draw like a little molecule here, so I'm going to draw a little molecule. And this molecule is called ATP. So ATP is a molecule of what is called adenosine, and it's attached to 3 little phosphates. So it looks like this. They got their own little chemical bonds, right? So it's ATP because this is what's called adenosine, which is actually, almost like it's a little protein, actually. And then these are phosphates. And then, like I said, there's 3 of them. That's where you get the tri from, right? So ATP, or adenosine triphosphate, right? So that's what this little molecule is. Now, think of this, do you guys know, has anybody ever heard how like, atom bombs work, like the atomic bomb, right? Like this thing that's kicked off the Cold War, we're all scared of it. What that is we learned how to take an atom, which is the smallest unit in the universe, right? And we learned how to break it in half. And, if you break anything, you break a stick, you hear a bunch of energy get released, right? Like you hear it go crack, right? That's energy being released, well, imagine taking, that stick is huge, imagine taking the smallest thing in the universe and breaking it in half. It causes a huge explosion because the universe is like, what happened? You broke something, and a bunch of energy got released. That's how atomic energy gets used. When we have like atomic, nuclear power plants, they're breaking atoms apart and they're capturing all the energy, and we're using it to power our computers and tablets and phones and stuff. So anytime you break a molecule, a bunch of energy is going to get released. So we don't want to be splitting atoms inside of our body. That would be too much energy. We'd blow up. But what we do want to be able to break is this molecule of ATP. So there's a whole bunch of energy trapped right here. There is a bunch of energy trapped in this little bond. That's a terrible arrow. I'm gonna erase that real quick. There's a ton of energy trapped in this little bond right here. So if you break it, right? If you break this bond, and I break this little bond right here, I kick this little phosphate off, a ton of energy gets released. That is how our body does everything that it does. Every single thing that you do is because you are breaking ATP molecules. The energy that's giving you, to be able to move your muscles, to breathe, to build stuff up, to break stuff down, all of that costs ATP. So you need to be able to make ATP constantly, because we can't just store energy in our body. If we tried to store energy in our body, we would just overheat and burn up, So instead, we store ATP, and then we break that ATP down, and that's what gives us energy to do work. So during oxidation, our body burns up molecules to create ATP, and then that ATP gets broken in order to allow us to do stuff. So, there's 3 ways that our body can make ATP. That process is what we call cellular respiration. So bringing in oxygen, changing the shape of another molecule, and creating a molecule of ATP, we call that cellular respiration. And it's not a perfect process. So because it's not a perfect process, there's some ingredients left over afterwards that we need to get out of the body. So if you bring in oxygen and you bring in glucose, so if you eat sugar and you breathe air, your body can take all that and make ATP. It's going, boom, there's some ATP, right? But then you've got a little bit of that sugar left over, and you got a little bit of that, and there's still a little bit of oxygen there. So what's going to happen is your body is going to attach that carbon, which is left from the sugar, to that oxygen. And now you're left with what is called CO2, carbon dioxide. You're going to get that out of your body. And that is why you inhale oxygen and exhale CO2. That is the process of respiration. Your cells are doing the same thing. So you're going to have like a little cell. You're going to have like, let's see, I'm just going to make a new drawing here. So that's what ATP is. So you're going to have like a cell here, right? And it's going to have its little cell components. And on the inside of the wall, what's going to happen is glucose, so sugar, is going to go in, and ATP is going to come out. Meanwhile, also oxygen. So glucose and oxygen are going to go in, and ATP and CO2 are going to come out. So, this is your product here, and this is your, byproduct here. And these are your ingredients. So we make energy by bringing in glucose and oxygen, and we spit out energy in the form of ATP, but we got a little bit left over. There's like some extra stuff, just byproducts, the grease left in the pan, in the form of CO2. And you've got to get that out of your body, and that's how you're going to exhale. So don't worry too much about that for right now. That's going to come back later. It's going to make much more sense later on in this class. But the 3 actions that make ATP in the form of cellular respiration are going to be glycolysis, what is called the Krebs cycle, and what is called the electron transport chain. So there are 2 ways that you can make ATP. Some of it can happen what is called anaerobically, which means an for opposite, aerobic for oxygen. So opposite of oxygen, it takes place without oxygen. So glycolysis is a series of enzyme reactions. A whole bunch of enzymes are taking sugar molecules and breaking them down into ATP. But there's one of the byproduct that's left over afterwards, you guys are very familiar with. In fact, you can make some of it right now. Let's say you need enough energy to allow you to do squats, right? So I'm going to do lunges, not squats. So let's say I'm doing some lunges here, right? And let's just say I keep doing this for the next 20 minutes, right? So what's going to happen is I'm burning up a lot of energy in my muscles, right? My muscles they need a lot of energy to do all this work. So what's going to happen is my body is going to produce lots and lots and lots and lots of ATP in order to allow me to do all that. And as I keep going, I'm making ATP, but there's some byproducts left over. In the process of glycolysis, the byproduct that's left over is lactic acid. I'm sure you guys are familiar with lactic acid. It's what makes your muscles burn like crazy, right? Where you're just like, oh God, it's starting to burn, you know, right? That takes place in the fluid portion of the cell. So in a cell, if we look at glycolysis, if you look at a cell here, glycolysis is going to take place, you know, hold on, right in this fluid area right here. It kind of just takes place kind of in all the goo. You know, your cells are kind of swampy. They're made mostly of liquid. So glycolysis is pretty much going to take place in all of this fluid stuff right in here. That's why it doesn't have any oxygen available to it. That's why it's called an anaerobic process. It's an anaerobic process because it doesn't require any oxygen. It takes place in the fluid. You know, it's like trying to breathe underwater. So your body makes a bunch of ATP, and then it also makes a bunch of that lactic acid. And here's the thing. We often think of lactic acid as a bad thing because it makes us burn. And you're like, oh God, lactic acid. Oh, I just want to get up the hill, you know? And you're just like, you're walking up the hill and you're just like, oh, it burns. Oh my God, you know? So we kind of, you know, a lot of people don't like lactic acid. But here's the thing. Lactic acid's awesome because it's going to allow you to produce more energy with these two processes right here. So after your body has produced a whole bunch of lactic acid, what's going to happen is that lactic acid is going to pass into these little guys right here. These are what are called your mitochondria. And they're where they produce a whole bunch of energy. Now, here's the thing. Your mitochondria needs to have oxygen in order to produce energy. So you can think of these, they're almost like little air bubbles inside of your wet, soupy, swampy cells, right? Your cells are filled with fluid, but these little mitochondria here, they got little pockets of oxygen. And so now an oxygen molecule is going to travel and it's going to work its way into the mitochondria here. And once it gets into the mitochondria, it's also going to bring in some of that lactic acid that we produced. So you produced lactic acid and you're bringing in oxygen, and that's going to pass into the mitochondria. And then the mitochondria is going to go through this process called the citric acid cycle. This is more commonly referred to as the Krebs cycle. It's named after this guy Hans Krebs. He's the one who discovered it. And that's going to produce some more ATP. So now lactic acid and oxygen go in from that initial glucose molecule, and it spits out some ATP. And then it's also going to go through another process afterwards. Actually, I'm going to skip forward here a little bit. It's going to go through this is what the lactic acids, the citric acid cycle looks like. So there's your lactic acid, and it goes through this big, long process here. And then you're left with a whole bunch of extra little hydrogen molecules here, all this little extra hydrogen. And that's going to go through what is called the electron transport chain. And the electron transport chain is also taking place inside those little beans they kind of look like, right? The little mitochondria here. So that's going to go through the electron transport chain right over here. And that's going to spit out even more ATP. So don't worry about it right now. I'm going to break this down way better in later classes. But what I want you to know for today is the process of cellular respiration takes place in two different versions. There's the aerobic version and the anaerobic version. And glycolysis is anaerobic. It takes place here in the fluid, okay? It spits out a little bit of ATP, and its byproduct is lactic acid. But that byproduct gets used in the next process, which is the Krebs cycle. So then lactic acid plus oxygen go through the Krebs cycle, and it spits out a little bit of more ATP. But it's also got some byproducts. And those byproducts plus more oxygen are going to go through the electron transport chain. And that's going to produce a whole bunch of ATP. So let's go back and we're going to finish up today's lesson by tracking how one sugar molecule is going to do all of this. So you eat something, and that sugar molecule is going to go into one of your cells, and it's going to spit out 2 molecules of ATP and a whole bunch of lactic acid. Then that lactic acid is going to go into the mitochondria. Then you're going to start breathing a little bit harder. And some oxygen is also going to go into the mitochondria. So we've got the lactic acid and the oxygen. And it's going to go through the Krebs cycle. And it's going to spit out 2 more molecules of ATP. So you've got a total of 4 now. 1 glucose molecule made 2. Now it made 4 ATP. So now that citric acid cycle, that Krebs cycle, is going to result in a whole bunch of this stuff called NAD and FAD. And NAD and FAD are going to go into the electron transport chain. And then you're going to breathe even harder, and more oxygen is going to come in. And that's going to go through the electron transport chain. The NAD and the FAD are going to come together, and that's going to result in about 32 molecules of ATP. And now it's all burnt up. You've got no more stuff. The only thing you've got left as a byproduct is a little bit of water because of dehydration synthesis and a little bit of CO2. And so the water is going to get expelled from the cell. The CO2 is going to get expelled from the body. And you can bring in some more glucose and bring in some more oxygen and keep that process going. And that is going to happen for the rest of your life. And I think that's super cool. So 1 sugar molecule goes in, it becomes a little bit of ATP, and it becomes a little bit of lactic acid. The lactic acid is going to become a little bit more ATP, and then you're going to be left with NAD and FAD. NAD and FAD are going to leave you with a bunch of ATP and a little bit of water and a little bit of carbon dioxide. And those are your byproducts. That is how our body catabolically breaks down food into sugars, and then it builds it back up into ATP, and then it breaks down the ATP in order to do squats and lunges and, give lectures on cellular respiration. So that is the whole process. So let's go ahead and summarize everything up today. Chemical reactions store and use energy in order to maintain life, right? Homeostasis, your ability to stay alive. And it performs all of your body's essential functions. The 2 main reactions of metabolism are catabolic, which is breaking stuff down, and anabolic, which is building stuff up. And that all takes place because of what we call oxidation reduction reactions. All of that stuff of like dehydration synthesis or hydrolysis. Hydrolysis catabolically breaks stuff down. Dehydration synthesis anabolically builds stuff up. And all of that allows us to, produce energy and do stuff, do work, right? And energy production is a different process called cellular respiration. Your cells breathe. They breathe in and they breathe out. They bring in oxygen, they exhale CO2. That allows them to produce energy and spit that energy out and do stuff. By the way, this is why zombies could never exist. I hate to do this. I hate to say anything about zombies, but the reason, you can't bring something back to life is it has lost its ability to produce ATP. Once that ability is gone, there's no bringing it back. I'm sorry. I know it ruins the world. I apologize. Frankenstein, the lightning bolt created a little bit of energy and they, got him back up and moving. Yeah, that can make the muscles contract once, which is why if you shock, dead tissue, it'll usually contract once, but it can't keep doing it because it can't produce energy anymore. Sorry, Mary Shelley.
No,
So,
that's fine.
What's that?
That's fine.
Yeah, you're like, I'm good without zombies. So those are the 3 processes. Glycolysis is anaerobic. That takes place without oxygen. And then the Krebs cycle and the electron transport chain, those are requiring oxygen. So those are aerobic. So we've got aerobic and we've got anaerobic. And that's what allows us to produce energy. And that is your first lesson. Like I said, it's going to be very technical for the first couple of days. I think we do that so that we can scare anybody. We can scare anybody away who's not sort of serious about studying this stuff. I promise we will get to how to do squats. We will get to how to pick the right number of reps and sets and stuff like that. But I want you guys to understand the biology and the physiology first before we get into any of that fun, running and jumping stuff. Do you guys have any questions today? Anything that wasn't clear in the lecture? Anything that's confusing? Questions for me? Comments? Concerns?
Okay, we want to do something homework for this kind of things now, or only
Not
to
today.
read all the videos in the
So,
canvas?
Study your notes. If I were you, my big tip to everybody, I always tell people to do this, get yourself a Sochi notebook and write. I know that I send you the notes. I'm going to send you the notes. They're all written down already. You could just print them out, but I really do recommend copying them and writing the notes down for yourself. That way you can write in the margins and, if you're like, this is what I think this means, you can put your own notes in there. You know what I mean? If you copy them,
for me, for example, I take a note, even if you have everything in the videos or notes or something, I take my own notes.
Yeah, that's a really good idea. So I recommend doing that. There is no homework today, but you should review your notes, review the PowerPoint. If you want to watch the video again, you can. But that's the end of the lecture. I always tell people you should do about 30 minutes to an hour of studying, and read the PowerPoints, read the notes, and review them. But I wouldn't do it right away. Take a half-hour break, let your brain cool down, and come back to it and start over. That's a much better way to study than just sitting and doing it all in one big chunk. Our brains do not absorb information in big chunks very well. We do much better when we break it down into pieces. So I definitely recommend doing that. Homework, official homework, like a 15 questions, will be tomorrow. So don't do homework 1 yet, because you will only have half the information. Homework 1 is going out tomorrow on day 2.
Okay.
Cool. Any other questions?
That's it.
Awesome. Kenny, you feeling good? Andre's a good question. Oh, how long is the class? This is a 12-day class. So we're going to be, we're going to have it for, this is day 1, 2, 4, and homework on 2, 4, and then midterm on day 6, homework on day 8, 10, final exam on day 12. And then we'll start nutrition, where we will talk about this again. Oh, it's about 8:30 to 10:30, 11 every day in terms of lecture. And then we expect you guys to do about an hour of studying afterwards. Homework days are a little bit longer, but that's about how long things usually take. Cool.
So today and tomorrow, today wanna be studied all the cellular metabolism, right?
Yep. And then watch, I'm going to put some links to some videos in today's email. I recommend watching those videos. They're kind of helpful. They move a little quick, but they're all about cellular respiration, so you can understand that. Links to the video I showed in class, plus a couple other ones.
Okay.
So, all right, guys, I'm going to go ahead and end the recording, and I'll see you guys tomorrow.